Hi, my name is Daniel Martin, and I will present our work ScanGAN360, a generative model of realistic Scanpaths for 360 images, which has been carried out at Universidad de Zaragoza in collaboration with Stanford University. Virtual reality is an emerging medium that unlocks unprecedented user experiences and has the potential to change the way we people consume content. However, and in order to convey a realistic and engaging experience, it is crucial to understand how people behave in virtual reality. This is a very challenging task and has been posed as a key problem in VR. In virtual environments, there is content in the whole 360 degrees around the user. Besides, and unlike traditional media, where content creators decide what to show, it is now the user who has full control of the camera. This translates into each user having a completely different behavior when viewing the same stimuli. Some works have tried to model visual attention in terms of saliency, where each region of the scene is assigned a value indicating how likely are users to draw their attention to them. However, saliency lacks temporal information. In this footage from Sitzman et al., we can see how every user, depicted in a different color, explores the same scene. In this case, each circle represents the exact point every user is looking at, and the region around it their field of view. As we can see, each user follows a completely different trajectory, even though they explore the same regions of interest. Each of these trajectories is called a Scanpath. Our goal is, for a given 360 scene, to be able to generate Scanpaths that mimic the behavior of real users while maintaining their variability. This can be of great relevance because capturing varied enough viewing data from people can be a very cumbersome task. It requires complex software and hardware setups to show content and to capture viewing data, and large amounts of participants whose viewing behavior has to be recorded for long periods. This task, at the end, requires hours and hours and just yields a limited amount of data. And this could also have a huge impact in many applications, such as narrative experiences, interior design, virtual avatars design, or rendering techniques and algorithms. Thus, in this work, we propose ScanGAN360, a new generative adversarial approach to Scanpath generation for 360 images. We adopt a generative adversarial approach, so our model is able to generate the Scanpaths in a non-deterministic manner. We follow traditional GAN training and feed our network with large amounts of real Scanpaths. We resort to a novel parameterization of Scanpaths, where each point is transformed into its three-dimensional representation in a spherical space, to avoid ambiguities. Additionally, and to ensure our model is able to learn the whole distribution of realistic Scanpaths, we optimize our model through a dynamic time warping loss function designed to work with time series. With all of this, our network learns how to sample different plausible Scanpaths for any unseen 360 scene. Please refer to the main document for further information on our model and training details. Let us first show you some results. So at the top left you are seeing a 360 scene. Bottom left shows a sample ground truth Scanpath, but remember that there are many more. And the right side shows three different predicted Scanpaths that resemble the ground truth one. Here, with the same arrangement as before, you can see how our predicted Scanpaths are similar to the ground truth ones, and tend to focus on relevant parts of the scene, such as the black cheese pieces. Please refer to the supplementary material for additional results in varied scenes from different datasets. Although some previous works have attempted Scanpath generation previously, they all present some limitations. We have compared to them in a set of scenes from different datasets and shown how our method is able to generate Scanpaths that are closer to the human ones. PathGAN is not able to focus on the most relevant parts of the scene. Saltiness trajectories are erratic and do not resemble the ground truth ones, and Su et al.'s model is biased towards contrast changes. Please refer to the main document and supplementary material for additional comparisons and an exhaustive quantitative evaluation on different metrics. We have also evaluated the ability of our Scanpaths to mimic the behavior of the human ones. We have analyzed the temporal and spatial coherence of our Scanpath, resorting to kernel density estimation. For a given scene, we have obtained a Scanpath from the points of highest probability of KDE at each time instant. This KDE yields a probabilistic map indicating what regions are more likely to be visited at each time step. In order to visualize this, we are also showing a viewport center in the point of highest probability. This way, we can see the most probable Scanpath for a given scene and how it follows a plausible trajectory while focusing on the regions of interest in the scene. Again, please refer to the main document for further details. We have also carried out additional behavioral evaluations analyzing the exploration time and speed of our generated Scanpaths or their congruency among others, and have compared them to those of the real ones. Additional details can be found in the main document. To conclude, we have presented a generative, non-deterministic approach to Scanpath generation for 360 images, resorting to a novel Scanpath parameterization and a novel loss function based on dynamic time warping. Our model is able to generate realistic virtual observers that behave as humans at a very, very low cost. You can find our code and model publicly available in our project page. Thank you.